Okay, in this lecture we're going to finish our section 1.5 material on integration by substitution. Just a quick reminder of what we had talked about in the last lecture. We used the method of substitution in order to integrate functions which either involve composite functions or quotients of two functions. And typically we would choose u to either be the inner function in the composition or the denominator if we're working with a quotient of two functions. So we did many examples of substitution in our last lecture. And in this next example that we're going to consider, we're going to see how substitution can be used to integrate certain functions which are going to come up repeatedly throughout the semester. And so we're going to derive formulas for some of these basic antiderivatives that we will use throughout the semester. And so these you'll want to have memorized. So before we go through this next example, let me just mention you might put a little star by this example in your lecture notes with a note to yourself that you want to memorize the formulas that we're about to derive in the next example. So in this next example, we are supposed to evaluate the given indefinite integral, and we're going to keep in mind throughout this problem that a and b are some non-zero constants. So in part A, we are asked for the antiderivative of e to the ax. So this is an antiderivative that will come up over and over again throughout the semester. So it's useful to derive a formula for it. So we see that this function is a composite function. It involves not just e to the x, but e to the a times x. So we're going to try a substitution. And typically we would choose u as the inner function in our composition, in this case a times x, in which case the differential of u would be a times the differential of x. And so solving for dx, we have du divided by the non-zero constant a. Looking at our integral of e to the ax dx, we can rewrite this in terms of u as follows. So we would have the integral of e to the u, and the differential dx on the end, we've said is equal to du divided by a. So I can factor out my constant factor of 1 over a, and I'm left with e to the u du. And we know how to handle this antiderivative. The antiderivative of e to the u is simply e to the u, and then we can add an arbitrary constant to get our most general antiderivative. And as with our earlier u substitution examples, once we have our antiderivative, we want it in terms of the same variable that we started with, in this case x. So substituting ax back in for u, we have 1 over a times e to the ax plus c. So this formula for the antiderivative of e to a constant times x, you'll want to have memorized. So some cases where this might arise throughout the course would be maybe integrals of the following form. Let's say we want to integrate e to the 3x plus e to the negative 4x dx. So rather than doing a substitution for each of these terms, if we make use of this formula that we just derived for a substitution, we know that the antiderivative of e to the 3x would be 1/3 e to the 3x, and the antiderivative of e to the negative 4x would be negative 1/4 e to the negative 4x, and then we can add an arbitrary constant on the end. Having this expression or this formula memorized will allow us to very quickly evaluate antiderivatives for these exponential functions that we'll see over and over throughout the semester. So let's look at another example. In part B, we have something similar, the integral of sine of ax plus cosine of bx dx, where a and b are non-zero constants. So again, we see that we're working with composite functions here, not just sine of x, but sine of a times x, and not just cosine of x, but cosine of b times x. So in order to handle this, we might first split this integral into two pieces. We know the integral of a sum is the sum of the integrals of sine ax and cosine bx in this case. And each of these integrals is a composite function, or involves a composite function. So in order to evaluate each of these, we're going to make use of a substitution. So in my first integral, where I have sine of ax, let me choose u as that inner function, a times x, in which case du is a times dx, same as in our part A example, and then dx is du over a. Now for this second integral, where we have a composite function cosine of bx, again I'm going to need to use a substitution. And since I've already used the variable u for a times x, let's maybe use another variable. Let's maybe call it w for the inner function in that second integral, that is b times x. So finding the differential of w, we would have b times dx. So dx in that second integral is equal to dw over b. So rewriting our integral in terms of u, we would have the integral of sine of u times dx, which we said was equal to du over a, plus the integral of cosine w times dx, which we found to be dw over b. So in my first integral, I can factor out a constant 1 over a. I'm left with the integral of sine of u du, plus from my second integral, I can factor out a constant 1 over b. We have the integral of cosine of w dw. And at this stage, we're ready to integrate. We know the antiderivative of sine of u du would be negative cosine of u. So with our constant 1 over a out in front, we have negative 1 over a cosine of u. And then plus, we have a 1 over b, and the antiderivative of cosine w would be sine of w. And then we can add our arbitrary constant on the end once we've found our antiderivative. And in the last stage, or last step, we're supposed to get our final answer in terms of x. So substituting u, which was ax, and w, which was bx, back into this answer, we have negative 1 over a times cosine of ax plus 1 over b times sine of bx plus c. Okay. So in summary, the antiderivative of sine of a constant times x is negative 1 over that constant a times cosine of ax. and the antiderivative of cosine of a constant, b times x, is 1 over that constant times sine of that constant times x. So as an example where these sort of integrals might show up, suppose we want the antiderivative of, let's say, cosine of 2x plus sine of 3x dx. Well, if we have these formulas memorized, the antiderivative of cosine 2x will be 1/2 sine of 2x. And the antiderivative of sine of 3x will be negative 1/3 cosine of 3x. In general, plus c. Okay. So let's look at some other ones. In part C, we will have another frequently appearing type of antiderivative where we're integrating 1 over ax plus b. So that is something of the form 1 over a linear function. So when we're trying to find an antiderivative of 1 over this linear function, we can make use of a substitution. So we see here that our function involves or the function that we're integrating is a quotient of two functions, or alternatively, we could think about this as ax plus b to the negative first power dx, which is a composite function, so that should also make us think of using a substitution. So let's see how we're going to handle this. In either case, we would choose u to be maybe the denominator, ax plus b, or the inner function in our composition, if we rewrote it in the second form, in which case du is equal to a times dx, and so dx is equal to du over a. So looking at our integral of 1 over ax plus b dx, we can rewrite this as 1 over u in the differential of x term, we said is du over a. So I can pull out a constant of 1 over a in front of the integral, and I'm left with 1 over u du. And we know what the antiderivative of 1 over u is. So we've got our constant 1 over a, and the antiderivative of 1 over u is the natural log of absolute value u plus some constant c. Or rewriting this in terms of x, we have 1 over a times the natural log of the absolute value of ax plus b plus some constant c. All right. So this is another formula that would be very useful to have memorized throughout this course. One thing that I want to stress about this integral is that this formula is only valid if our denominator is a linear function. So students will often make the mistake of using this formula if they have something of the form, say, 1 over a quadratic, but that does not hold. This formula is only valid if the denominator is that linear function of the form ax plus b. So to see an example of where this might arise, let's suppose that we have an integral like this. Maybe we have 2 over 4x plus 7 minus 1 over, let's say, 6 minus 3x dx. So we'll see antiderivatives of this form a bit later in the course. And so how can we use this formula to handle this? Well, we see that our first term in this integral is a fraction where our denominator is a linear term. Now the fact that our numerator is 2 doesn't really matter because we know that we can pull a 2 out in front of our integral. So we're left with 2 times the integral of 1 over 4x plus 7 dx, and then we're subtracting the integral of 1 over 6 minus 3x, which is also a linear function. So once we have these two integrals where we have 1 over some linear function, we know using our new formula that the antiderivative is given by the natural log of the absolute value of that linear function. And then out in front of the logarithm, we're multiplying by 1 over the constant a. That is 1 over the slope of that linear function. So in this first piece, we had a 4x plus 7. So out in front, we're going to be multiplying by a 1/4, or our 2 over 1/4 becomes 1/2, the natural log of 4x plus 7. And then we were subtracting on the end the integral of 1 over 6 minus 3x. So again, using this same formula, we would have the natural log of that linear function, 6 minus 3x, and we multiply out in front by 1 over the slope of our line. In this case, negative 1/3. So since we're subtracting that value, this becomes a positive 1/3 times the natural log of 6 minus 3x, and in general, we can add a plus c on the end. All right, so one other type of integral that will show up somewhat frequently that is useful to have a formula for is something of the following form. Part D, which is the integral of 1 over x squared plus a squared dx. So before we look at how that integral will be evaluated, let's recall a formula for an antiderivative that you saw in Calculus 1 that you may not have thought about for a while. So the antiderivative that we're going to make use of is the following. The integral of 1 over x squared plus 1 dx is arctangent of x plus c. Because remember, the derivative of the arctangent function is this 1 over x squared plus 1. So the antiderivative of that would be the arctangent function. And what we have in our problem for part D is very similar. We have 1 over x squared, but not plus 1. Here we have plus a squared for our denominator. So in order to evaluate this, we want to try to make this function look more like the antiderivative for arctangent. And the way that we can do that is by factoring an a squared from each term in the denominator. So if I factor out an a squared from the denominator, I would be left with x squared over a squared plus 1 dx. And from there, I can take the constant factor of 1 over a squared out in front of my integral, and I have 1 over x squared over a squared plus 1 dx, which I could rewrite as 1 over a squared times the integral of 1 over x over a quantity squared plus 1 dx. So all I'm doing so far is rewriting the form of my integrand. I factored out an a squared from the denominator, and after that, the term x squared divided by a squared, I just rewrote as a single fraction x over a quantity squared. So when I get to this stage, I've got a composite function. Notice that my denominator involves the composition x over a quantity squared. So when I see that composite function, I'm going to make use of a substitution. So let me call u x over a, the inner function in my composition. So that du is given by 1 over a dx. And then solving for dx, I would have a times du. So going back to our integral of 1 over x squared plus a squared dx, we're going to rewrite that as follows. So remember, out in front we had a 1 over a squared times the integral of 1 over, now x divided by a is what I was calling u, so I have 1 over u squared plus 1, and then the differential dx on the end we said is equal to a times du. So taking a times du, now I can simplify a little bit. I have a constant factor of a, which when I bring out in front of my integral and multiply by 1 over a squared, I can cancel one factor of a, and I'm left with 1 over a times the integral of 1 over u squared plus 1 du. And so finally, at this stage, we notice that this integral, or this antiderivative, is exactly the formula for, exactly arctangent. So what we're left with is 1 over a times arctangent of u plus c, or 1 over a times arctangent of u, which was x over a, plus c. And this is a useful formula to have memorized for some integrals that will appear frequently later in the course. So as an example of the type of problem where this might appear, let's say that we have something like the following. Maybe we need the integral of 1 over x squared plus 25 dx. So we have 1 over the sum of squares, x squared, and 25, which is 5 squared. So this has exactly the form of this integral that we were just looking at, where a is 5. So using this formula that we derived, our antiderivative would be 1/5 times arctangent of x over 5 plus c. Okay. So those types of integrals will appear frequently later in the course. So it's very useful to have these formulas that we've derived in parts A through D of this last example memorized. It'll be worth your time to memorize those. Now, to finish out our section 1.5 material, we're going to look at some examples where we'll evaluate a definite integral by using substitution. So in all of the examples we've been considering, we've been looking at indefinite integrals. That is where we're just finding the most general antiderivative. And in these last couple of examples, we'll consider definite integrals, which might be used to represent, say, the area under the graph of some function. So let's see how the process of substitution would be used for definite integrals, and make a little comment about notation. So looking at this first one, part A, we're asked for the integral from e squared to e cubed of 1 over x times the natural log of x squared. So I know from the fundamental theorem of calculus, to evaluate this definite integral, I need to find an antiderivative, and then I'm going to evaluate that antiderivative at my endpoints. So in order to find an antiderivative or to integrate this function, we would need to use a substitution. So we see here that our denominator involves a composite function, the natural log of x quantity squared. And that should immediately make us think of trying a substitution where u I'm going to choose as the inner function in that composition. That is the natural log of x, so that the differential of u is given by 1 over x dx. And then solving for dx, we would have x times du. Okay. So let's look at our integral. Now, before I rewrite my integral in terms of u, something that I need to be careful of is the fact that these limits of integration, e squared and e cubed, are values of x. They are not values of u. So something that students tend to do is write this integral as follows. They would say this is then equal to the integral from e squared to e cubed of, let's see, this works out to be du over u squared. However, this is incorrect. Why is this incorrect? Well, these limits of integration, e squared and e cubed, if you use this notation, that would mean that those are the values of u, not x. So if we're working with a definite integral and we're making a substitution, part of the problem is to change those limits of integration, which were values of x, into their corresponding u values. So let's see how that's going to work here. So let's start by looking at our lower limit of integration, which was x equals to e squared. Now, if x is equal to e squared, then u is given by the natural log of x, so the natural log of e squared, or 2. And for our upper limit of integration, which was x equals to e cubed, we find that u, which is the natural log of x, so the natural log of e cubed, would be 3. So once we have the u values that correspond to our x values given in the problem statement, we're ready to rewrite our integral. So the integral that we were given was the following. So rewriting this in terms of u, let's start by changing the limits of integration. So our original value was x equals e squared. We saw that that value gave us u is equal to 2. So the lower limit of integration in terms of u will be 2. And our upper limit of integration, e cubed, well, we found when x was e cubed, u was 3. So our new upper limit of integration in terms of u will be 3. And now we are left with 1 over x times u squared. And then dx, we said, was equal to x times du. So we see that our factor of x in the numerator and denominator cancels. And we're left with the integral from 2 to 3 of 1 over u squared du. So we now have a definite integral in terms of u that has the same value as the integral that we started with. And to evaluate this, using the fundamental theorem of calculus, we have to find an antiderivative of 1 over u squared. So if you prefer, you can rewrite it as u to the negative 2 power du. And it follows from the power rule that the antiderivative would be -1 over u, which we then evaluate from 2 to 3. So a couple of comments here. First off, notice I did not include the plus c here. Why not? Well, we're working with a definite integral, and the fundamental theorem of calculus said that we can use any antiderivative we want. So I'm going to use the one where that constant of integration is 0. Or I just recall that for definite integrals, I don't need that constant of integration. Now another comment here, in the cases that we were working with earlier for indefinite integrals, I would substitute my expression for u back into my antiderivative. Now that's not necessary here. Why not? Well, because these values that I'm going to be substituting into my antiderivative, I've already changed to values of u, not x. So these numbers 2 and 3 are values of u, not x. So I don't want to substitute u back in here. Instead, I just want to substitute the values for u directly into this antiderivative that I just found. So we would have, when we substitute 3 in for u, a -1/3. And then we subtract the value that we get when we substitute 2 in, which would be -1/2. So subtracting the -1/2, we have +1/2. And so -1/3 plus 1/2 leaves me with a value of 1/6. Okay. So the point I want to, or a couple of points I want to make with this first example using a substitution for a definite integral. First off, I want to mention that we need to change those limits of integration from x values to u values. So that's an important point. And then recall that for definite integrals, we don't need to include the constant of integration. So that is omitted here for this definite integral. And in the last step of our problem, instead of substituting our choice for u back into our antiderivative, I'm going to leave my antiderivative in terms of u. And the reasoning for that, again, is that we've already changed our limits of integration to u values. So I just want to plug in those values for u directly, instead of going back to everything in terms of x and then plugging in those x values. So it would sort of undo the work that we had done in the first step of our problem. So let's look at another example of this to finish out this section. So in part B, we have the definite integral from 1 to 9 of 1 over the square root of x times e raised to the square root of x. So when I'm looking at this example, what is it that makes me think substitution? Well, it's the fact that this denominator involves a composite function. It's e raised to the square root of x. So when I see that composite function, that makes me think of a substitution where u will be chosen as the inside function in my composition. In this case, the square root of x. So the differential of u is then 1 over 2 times the square root of x times dx. And so solving for dx, I would have 2 times the square root of x du. Now, because this is a definite integral, I also need to change my limits of integration, that is 1 and 9, from values of x into values of u. So let's take a look at that here. For our lower limit of integration, x equals to 1, we have u is the positive square root of 1, which would be 1. And if x is equal to 9, our upper limit of integration, then the corresponding u value is the positive square root of 9, which is 3. So the integral that we started with, that is from 1 to 9, of 1 over root x e to the root x dx, can be rewritten as the integral from, let's look at our u values. So when x was 1, we said u was 1. So our lower limit of integration for u will be 1. And we said when x is 9, our upper limit of integration, then u is 3. So our new upper limit for the integral is 3. And we're now left with 1 over the square root of x times e to the u power. And then dx, we said, was 2 square root of x du. So we see that this root x term in the numerator and denominator cancel. I'm left with a constant factor of 2, which I can bring out in front of my integral. And then I have 1 over e to the u du. So how can we find an antiderivative of 1 over e to the u? Well, we can simply rewrite it as e to the negative u power. And now this antiderivative looks exactly like one of the formulas that we just derived. Recall from our previous example, we just said the integral of e to the ax dx is 1 over a e to the ax in general plus c. So here we have e to the negative u du. Well, that's exactly this formula where a is equal to negative 1. So our antiderivative is then negative 2 e to the negative u. Since we had a constant 2 out in front already, just multiplying it by that negative 1, we have this negative 2 times e to the negative u power. And we're evaluating this antiderivative from 1 to 3. So again, here we don't need the plus c term because this is a definite integral. And I don't need to get my antiderivative in terms of x because these values, 1 and 3, are values for u. I want to plug those into this antiderivative directly. So let's see what we have. We have a constant out in front, negative 2. When I evaluate this antiderivative at 3, we have e to the negative third. Then we subtract what we get when we evaluate the antiderivative at 1, which would be e to the negative 1. So we have the following expression for this definite integral. So again, in part B, the point I'm trying to stress here for u substitution with definite integrals is that we need to change our limits of integration in terms of x or whatever variable we're given into the corresponding values in terms of u.